So, our last invited speaker today is Yann LeCun, the director of Facebook AI Research and professor at New York University, and he will be speaking about energy-based GANs and other adversarial things.
So this is going to be a little bit of a beginning with a recap of some of the stuff I talked about during the keynote, but maybe in more details, maybe with a little more information, also with some very recent results, which I kind of alluded to during the talk, but not really in any detail. So let me first talk about, sort of come back on to the connection between unsupervised learning in general and, or at least unsupervised energy-based learning and adversarial training. So you can see adversarial training as the idea of, not adversarial training, unsupervised learning as the idea of trying to capture dependencies between variables. So let's imagine a very simple case where we have just two variables and the points that we are observing are along this curve. So what that tells you is that if you know the value of y1, you can pretty much predict the value of y2. If you know the value of y2, you might be able to make a guess as to two alternative values for y1, because there are two possible ones in general here. And having captured this dependency allows you to predict any subset of variables from any other subset. So what you need to do, be able to do this, one way to be able to do this is to learn some sort of contrast function that tells you whether you are on a manifold of data or outside a manifold of data. And this contrast function, you can call it an energy function. If you believe in the maximum entropy method, you can think of a probabilistic model that would be derived from this energy function through a Gibbs distribution. But in fact, since we never normalize those functions, we don't actually need to ever take the exponential and normalizing. So we'll just stick with the energy function in the first place, and that's the basic idea behind energy-based models. Kind of throw away the baggage of probability theory. But then you have to be careful because you also throw away all the constraints of probability theory that prevent you from making mistakes. So it's a little more adventurous if you want. So you want to train a contrast function to tell you whether you're on the data manifold or not, that takes low value on the data manifold, higher values everywhere else. And of course, it's very easy to parameterize a function. So basically a function that takes a vector, produces a single scalar, and it's very easy to train that function so that when you give it a piece of data, it gives you a low answer, a low value, a low output value. You just do that by gradient descent, right? Show the samples. Every time you show the samples using stochastic gradient descent, tune the parameters so that the output goes down. The main issue is how do you make sure the energy outside of the manifold of data is higher? And that's where all the unsupervised learning algorithms differ from each other in this kind of general interpretation. So what you want is some learning process that sort of shapes the energy function a little bit in this form. And by the way, this works whether the process is supervised or unsupervised. The only difference between supervised and unsupervised learning is that in supervised learning, you know which variables are known in advance, and you don't know which ones you need, and you know which ones to predict. Whereas in unsupervised learning, you don't really know which ones will have to be predicted from each other. That's kind of one of the differences. The other differences, which is not really a qualitative difference, but more of a quantitative difference, is the fact that there is uncertainty in the output. So here, for example, in this example, it's very easy to compute. If I go back to this diagram, it's easy to predict y2 from y1, but it's much harder to predict y1 from y2 because there are two possible values. And so it would be kind of a standard supervised learning problem if you were asked to produce y2 from y1, but if you were asked the other way around, then you have to deal with the uncertainty in some way. So it's easy if the distribution is discrete. It's not that easy if it's continuous, particularly if it's high dimensional and continuous. And those are the problems we're interested in if we want to model kind of complicated things about the world. So the question is, how do we make the energy higher outside of the samples? And I flashed this slide during the keynote, but let me go a little bit through that again. So you can think of most of unsupervised learning algorithms as being different strategies to make the energy outside of the manifold of training data high. You can do things like traditional methods like PCA or K-means or Gaussian mixture models, square RCA. And what all of those methods do is that they don't explicitly push up on the energy outside of the manifold of high data density, they kind of limit the volume of stuff that can take low energy by design. Either in the case of a gas and mixture model, because it's normalized, because it's a normalized probability distribution. In the case of PCA, because it's a linear subspace, so everything that's outside of the linear subspace will not be reconstructed, and so the reconstruction energy will be higher outside of the principal subspace. In K-means, only the prototypes are correctly reconstructed. The reconstruction energy is 0 on the prototypes, but it grows quadratically as you move away from every prototype. So you get this kind of diagram where this is the energy function for PCA, where here the data samples are sampled along this, this spiral. And if you apply PCA to it, you'll get the principal axis of the spiral, which is a very bad model for the spiral. And as you move away from the principal axis, the energy, which is the reconstruction error, goes up. It's the distance between a point and its projection on the principal axis. For K-means, the reconstruction error, of course, is the distance to the nearest prototype. So what you get is kind of this landscape in which you have quadratic wells centered around the prototypes, and then the energy goes up outside of that. And that, of course, works really nicely in low dimensions, like in this example, but it doesn't really scale up to high dimensions. If you want to kind of put prototypes everywhere in the space in high dimension, it really doesn't. You can't interpolate very well. So here is another idea. You just parameterize this energy function in such a way that you push down on the energy of data points and you push up absolutely everywhere else. And you can push up on everywhere else by computing some sort of integral of the energy, or the exponential minus the energy, something like that, over the entire domain, and then computing the derivative of this with respect to the parameters and push up. This is what maximum likelihood does to you. And if this integral is, which is the partition function, is tractable, it works. But in most interesting cases, it's not tractable, and so you kind of have to give this up. One way to get around this is to use variational bounds, and so you approximate this integral using a surrogate energy, if you want, or log probability, and you kind of push on that one with the hope that it will work. But let's go to number 3, which is pushing down on the energy of data points and pushing up on well-chosen locations outside of the manifold of data. And now the question is, how do you pick those points? So, for example, you have contrastive divergence. It's been popularized in the context of RBMs, but it's actually a general idea. The general idea of contrastive divergence is you start from a data point. The simpler form of contrastive divergence, you start from a data point, and then with some noise, you go down in the energy landscape of your model. And so if your model is correct, most likely the point will stay more or less where it is, maybe move a little bit. But if your model is incorrect, there is going to be a region where the energy is lower than where you started from. And so your point is going to move down this energy surface, and that point you're going to move up. Okay? If it stays in the same place, you also move that up, but since it's going to be compensated by being moved down, when you actually show the data point, you have a kind of a balance of those two terms. So that's the idea of contrastive divergence, and the idea is that you don't run this process of kind of moving down the energy for too long, you just kind of limit its size. If you run it for a very long time, that's basically Markov-Chain Monte Carlo approximation of the gradient of the partition function. There's a number of other methods that kind of use similar ideas, but that's sort of the idea. So basically you need an intelligent process to generate points outside of the manifold of data whose energy you're going to push up. And I'm going to just say right now that adversarial training uses a neural net, a generator, to generate points in an intelligent way whose energy will be pushed up. Okay? So let's kind of keep this in mind for a bit, and I'm going to talk about other methods now. So one way, I'm going to skip number 4 because it's really impractical for complex models, but there's a method that was popular in the mid-2000s when many of us were working on deep learning originally, which is to essentially train, this is number 6, use a regularizer in your model that limits the volume of space that has low energy. So you don't build it by default like in PCA or K-means, but you sort of put a term in your loss function that you minimize, or your energy function that is computed by the model, in such a way that the volume of stuff that can take low energy is limited. And that's the idea behind sparse auto-encoders. So in a sparse auto-encoder, you say, I start from an input, I go to a code, and I make this code sparse, which means I limit the number of configurations that code can take. And what that does is that it limits the number of points that can be properly reconstructed, because the number of configurations that is allowed in the code is relatively small. So only the point that have an exact code will have a low reconstruction energy. So the energy is the reconstruction energy. And imposing sparsity says make the volume of stuff that takes low energy as low as possible, essentially. And there are other ways to do this. So variational autoencoders, for example, use a similar ploy, which is instead of sparsifying the code, you add noise to it. And by adding noise, you kind of limit the amount of information that's carried by the code. And in effect, what you're doing is you're limiting the volume of stuff that can be exactly reconstructed. So it's kind of another interpretation of variational autoencoders, if you want. And that idea, by the way, goes back to early work by Michael Lewicki in particular on sort of adding noise to the middle layer of an autoencoder. He was in the linear case, so. So that's a couple kind of methods that can be all explained a little bit in this term of, pushing down and pushing up on energies in various ways. So in the case of sparse coding or sparse autoencoders, this is the kind of energy surface that you get. You take a point, you encode it to kind of a sparse representation, and then you reconstruct with a decoder, all of which can be neural nets. And what happens if the decoder is linear, then the reconstruction essentially is linear, of course, and so that corresponds to having a linear subspace for every set of code units that are active. So if you take a particular set of code units, you vary the values. That means the code moves around a linear subspace, and because the reconstruction is linear, that means the reconstructed image also lies in the linear subspace. And when you change the active units in the code, you change the linear subspace. So what you get is an energy function that reconstructs properly things that are on those linear subspaces, but then you get higher reconstruction error outside of those subspaces. So you get this kind of energy function. So what I've said so far is that essentially adversarial training is a way to generate contrastive points in a smart way. And the way it's smart, so you could think of it as if you were to compare, for example, Markov-Chain Monte Carlo methods, which have contrastive divergence, to generate contrastive points, and adversarial training, you could think of Markov-Chain Monte Carlo methods as being a kind of a non-parametric way of generating points that use the model itself. And you could think of adversarial training as sort of a parametric way of generating those contrastive points, because you're going to train a neural net to generate those points. Right, of course the generator is the one you're going to train to generate those contrastive points. But then there is another view of adversarial training, which I'm sure you've heard about today or before by reading papers, which is that you really have two interpretations of adversarial training. The first that I mentioned is one in which the thing you want to train is the discriminator. The discriminator is your likelihood model, if you want, or the thing that tells you, the contrast function that tells you whether you're on a manifold or not. And the generator is just a smart way to generate contrastive points. But you have another view, which is what you really want to train is the generator. And what the discriminator is simply a trainable objective function for it. An objective function that says, I'm not going to specify exactly which output you should produce, but I'm just going to say, any of those points that lie on the surface, which is characterized by the discriminator saying the energy is low, are okay for this situation. So it's really the view of a trainable objective function that allows for some slack in the output. So if you don't know what the desired output of a system should be, but you have some way of characterizing what it should be through training by training a discriminator, this is what you want to use adversarial training for. So in this form of adversarial training, of course, you do the classical adversarial training procedure where you take a point from the data set, you run it to the discriminator, you tune the parameter of the discriminator so that its output goes down, the energy goes down. And then you make the generator generate a point, it has access to a source of random vectors. It generates one of those green points, and you train the discriminator to make its output larger for all those points. So one thing that's important to note here, you don't want the discriminator, the loss function that the discriminator is going to optimize, to push up those points to infinity. You want the discriminator to push up its output to some level, but you don't want to push it up to infinity. And that will be important for the design of the loss function you want to use, because now we're not using probabilities that are bounded between 0 and 1 anymore. We have a choice of all kinds of loss functions, so we have to be careful which one we choose. That kind of makes sense in this context. And then, of course, there is a procedure by which the generator trains itself to generate those green points as close as possible to the blue points by getting the gradient of the discriminator with respect to its input and then adjusting the parameter of the generator so that the green points get closer to the blue points. In other words, so that the green points, when fed to the discriminator, produce a low output of the discriminator. Okay, so it's very intuitive, really, when you kind of think about this for a bit. And what that buys you is that it allows you to design the discriminator in ways that you may not have thought if you thought it had to produce some probability output. So in particular, one of the things we've used in the paper that is submitted to Aclia, it's on archive. One of the structures we've used as a discriminator is an auto-encoder, where the energy, the output, the ultimate output of the discriminator is actually the reconstruction error of this autoencoder. So beyond that, it's just normal EBGAN. So the loss function is a little funny. It's sort of a hinge loss-like thing, and I'm going to go into this a little bit. Okay, so first of all, I'd like to explain a little bit why the motivation for using an autoencoder, which may or may not be true, but it's an intuition that we're trying to kind of verify with experimentally. And the intuition is this. When you train an autoencoder, the gradients that you propagate through the autoencoders span a large space, because they basically span the space that of the targets of the autoencoders, which is the input is supposed to reconstruct. When you train say a convolutional net or something like this, to just produce a single scalar on the output, the gradient that you get is very degenerate, is very poor. Because you're only asking the system to kind of predict a single scalar without giving it any extra information. And so when the gradients propagate to the network, you just have one scalar that's different from one example to the next. Of course, the nonlinearities in the network will make the gradients different, but the gradients will probably span a relatively low dimensional space of the entire space. And there is kind of a good chance that it will be much larger in the context of if you use an autoencoder for that. There's another advantage, which is that an autoencoder has a code inside on which you can apply all kinds of constraints. Like you could force the code of the autoencoder to be different for all the samples within a mini batch. This is one of the tricks that we use in the paper to make sure that the function is not unimodal, and that actually forces the generator as a consequence to actually generate diverse inputs and not just focus on one mode. Okay, so let me talk about the loss function a little bit. So in effect, the properties of the loss function you want to use, you really have two loss functions. Okay, there is a way to formulate GANs in which you use the same loss function for the discriminator and the generator, really. And that loss function is being minimized by the discriminator and maximized by the generator. And that doesn't quite work because you kind of have to bound those loss functions, and it might be a little unstable. So in fact, you don't actually have to use the same function, and in practice, people don't. And so here is kind of a slightly general formulation. There are more general than that, but a slightly general formulation of the loss function for an energy-based GAN. One in which the loss of the discriminator has two terms. One, of course, is you want the output of the discriminator on the real data, which is f of d of x, to be as low as possible. So f is a scalar loss function, which can be the identity function or something like that, or a square or whatever. In fact, it could be any convex, monotonically increasing function such that f of 0 equals 0. So f of d of x simply says make the output of the discriminator as low as possible on the real data. And the second term, f of the positive part of m minus d of g of z, says make the energy produced by a generated sample be at least m, where m is some arbitrary margin that you pick. Okay? So this is sort of like a hinge loss, the same kind of stuff you would use for a supervector machine or something like that, or you know, some weak form of, you know, in fact, you could use the same loss as in logistic regression, except m is infinite in that case. So we're going to use a loss function of this form for the discriminator, and then for the generator, it's the same f that you apply to the output of the discriminator, but now you're going to compute the gradient of this with respect to the parameters of the generator. So here are two plots that are examples of those loss functions, where f is the identity on the left or is the square on the right. If we assume that d of x is positive, then how the function behaves on the negative part really doesn't matter. And here is a result that was proved by Michael Mathieu, who's a student with me at NYU. And what he proved is that there is a Nash equilibrium to this dynamic process. So if you minimize those two functions with respect to the parameters of both the discriminator and the generator, there is a Nash equilibrium. And if your learning process reaches this Nash equilibrium, then the distribution produced by the generator will be identical to the distribution of the data, under some assumptions of, you know, realizability and things like that. So that's cool because, you know, it says you're not kind of completely driving blind. You have some guarantee that the functions having the right form will actually lead to something useful. Now, there is very likely a more general form of those loss functions. Here we just used a hinge, but anything that basically is decreasing or would probably work. So I showed those examples in my keynote, so I'm going to skip, and I showed a little bit of the video prediction as well, so let me skip ahead. I'm going to talk a little bit about a poster that was presented by a large collection of my students and postdocs from NYU about style transfer. And it uses adversarial training in a very interesting way, which is to kind of sort of transfer style from content, if you want. So kind of being able to take a picture whose category you know, and then another picture, perhaps with a different style, and then kind of transfer the category of one with the style of the other. And the architecture is quite complicated. There's basically on top here two autoencoders, or the top is an autoencoder. So you take an image, run it through an encoder, and the code has two parts. One part that you think you know, say a label, and another part that you may not know, okay? Say a style, pose, etc. Okay, so the one that you know is denoted S, and the one you don't know is denoted Z. And you run those two codes through a decoder, and then at the end you tell the autoencoder just reconstruct the input. Okay, the second row of module says I'm going to swap the style or the part I don't know about the image. So I'm going to take another image of the same label, x1 prime, run it through the encoder. I'm going to discard the style part, and then take the style part from the other example, feed it to the decoder, and then reconstruct. And what I should reconstruct, of course, is the first example, not the second example, because those are two examples of the same category, but I'm feeding the style of the first sample. So what my encoder-decoder should reconstruct is the first example, not you know, x1, not x1 prime. And then there is kind of a third thing where, again, you take the unknown part of x1, and you show an example from a different category altogether. And you don't know, of course, what the reconstruction should be, because you don't know how the, you know, pattern of class x2 with a style of x1 should look like. And so the only thing you do here is reconstruct through an adversarial loss. So basically a discriminator which is trained in a normal way with real data and generated data. and it's trained to tell you whether the reconstruction, the prediction looks nice. And you kind of have to add another one, which just allows the system to kind of just generate sample for category 2 with any style it wants. You have to train this whole thing all together. And if you do this, you can do pretty amazing things like transfer the style to the given category or vice versa. So here at the top, you have a bunch of characters of different categories. And then on the left column, you have characters of different styles. They actually are the same characters. And each of the characters in the matrix has the category of the column and the style of the row. So if you look at one row, it's basically all the character categories in the style of the character to the left. Okay? And you can do this because you have this sort of factorial code, disentangled codes for category and style here. So you can take a character, 2 characters, and then use the content for one, the style for the other, and what you get is a swap of the 2. You can interpolate, so you can take 2 characters, the one at the upper left and the one at the lower right, a 1 and an 8. And they both have a content and a style. And you can try to kind of warp so interpolate the content from left to right, from the 1 to the 8. And so you get each row is such an interpolation. And then vertically, you interpolate the style. So as you go down, the 1 kind of gets more slanted because the 8 is slanted. And as you move to the right, you get something that's more like an 8 than a 1. Of course, that works on kind of slightly more complex images, like little sprite characters from video games. This is a data set that we used by our friends at University of Michigan, where you can also do kind of style transfer, and you can interpolate as well. And one cool thing that spontaneously appears is that if the unknown part basically ends up being the pose, which you don't have to force, you can do things like this, where this is on the NORB data set, and it's kind of difficult to make it work in this case, but again, you have each column is a different category, and now what the system tries to reproduce is the style, which consists of illumination and orientation. And what's kind of cool is that the system figures out what sort of a canonical orientation of each category is. So regardless of whether the object is an airplane, an animal, a person, a bus, or whatever, if you look at the 4th row, for example, they're all objects of all those categories, but all viewed from the top and slanted at a particular angle. So it's kind of figured out what's common about orientation between all of those objects, like where the head is, where the tail is, and things like that, without any supervised information about orientation, which is kind of cool. And you can do this for natural images as well, with sort of face, so transfer the face of a person to another one, as well as the orientation of the face or the style of the background. That's what I have in terms of material. But one thing I want to say is that there is a lot, as you probably know, because you're here. There's a lot that we don't understand about GANs. And I think what we need to do is really kind of simplify what the concept of GAN is to kind of really understand what's going on. I'm reminded a little bit of the situation we were in the late 80s, early 90s, where a few people had kind of figured out how to train neural nets, and the vast majority of people, when they were trying neural nets by themselves, couldn't make them work. And that's one of the reasons why neural nets came out of favor in the early 90s. It's because a lot of people just couldn't figure out how to make them work and didn't kind of try hard enough. And at the time, nowadays, it's customary when you write a research paper or something, you distribute your code with it so other people can sort of profit from your experience. But back in the 90s, early 90s, there was no internet, if you remember, if you were born. And there were FTP and things like this and email, but everybody used different software platforms and different hardware platforms. So there was no way to really port software. It was very difficult to write those things, so people were kind of a little jealously guarding them. And so what happened is that a few groups that had the right tools figured out how to train neural nets, and they had a reputation of being the only ones to be able to do this, and then most people kind of gave up. That's one reason why neural nets fell out of favor, in my opinion, in the mid-90s. because you always have to ask the question, why did it happen? And we have to be careful that this does not happen to GANs, because they are kind of finicky, but we're going to figure it out eventually. And I think they're extremely promising. As I said in my talk, it's the best idea in machine learning in 10 years or 20 years. I'm not sure if it's 10 or 20. We need to keep at it. There's a lot of theory that needs to be done, and there's a lot of people, very smart people in the room here and outside who can help with that. Thank you very much.
Are there any questions?
So you did mention that you think of the generator as an intelligent way of generating these points where you want to push up the contrast function. What makes you say it's intelligent? So what in particular is intelligent about it?
Yeah, it's kind of a, half of a joke, tongue-in-cheek. They're intelligent because it's a big neural net that you train, right? No, I mean, it's intelligent in a way that the neural net can learn the structure and the geometry of the surface, and sort of take advantage of the regularities in this surface, which a blind algorithm like MCMC just can't, right? So of course there are ways to kind of use MCMC in ways that are smart, like persistent CD, for example, where you have a bunch of particles that kind of move in the space, and whenever they fall in one place, you push up the energy of that, and so they kind of roll down in another region, etc. Those tend to be relatively efficient for RBMs, but it's still very blind. It doesn't capture any kind of grand structure about the function. Whereas when you train this neural net to generate those points, you might hope that it will capture some sort of regularity about it.
Hello? Is it working? So I was also struck by the example where you copied the orientation of one object to another. Do you know if it uses the shadows in the pictures to do that? Because I couldn't figure out how it would do that.
I don't know. We haven't done any analysis of this. We don't know how it does it. Michael is sitting right behind you. Maybe you can answer that question. I don't want to put you on the spot, but I don't know, really.
I have a question. Could you comment on the differences or similarities to the, there's the style transfer work from Kingma and colleagues, NIPS 2 years ago, 2014. Can you sort of comment on how those...
I mean, there's a long history of style transfer. Actually, I think the first paper of Josh Tenenbaum at NIPS, which must have been like 15 years ago, actually used tensor factorization for style transfer. Yes. So, it's not like style transfer is a new idea or anything. The idea of disentangling or factorizing representations is really cool. Generally, it's done supervised. So the advantage of this technique is that you don't have to specify the style. The only part, you only have to specify the part that you know, and then the rest is whatever is left. So actually, maybe this is a senior moment, but I don't actually remember exactly what technique they used in this paper you mentioned. But
it's similar in that sense that they provide one part, like here, like the class label, but not the style. And the examples are sort of very similar of also the MNIST and different writing styles across the different digits. And,
right. So,
it seems pretty close.
What I don't remember is the exact architecture and criteria. But one thing that's also similar is what people in computational neuroscience called slow feature analysis. So you have two images that are, say, two successive frames from a video, and you assume that the content hasn't changed, basically the same object, it's just in slightly different positions. And you sort of try to train a feature extractor in such a way that it eliminates, it's invariant, so that it eliminates the motion and so it keeps the identity. In fact, we had a paper, Michael also a co-author on this, last year, I can't remember if it was actually or CCV or NIPS or whatever, but on this idea where you can use successive video frames with an autoencoder, and you have some criterion that says, I'm going to compute some invariant representation, and I want that part to be constant over time, or easily predictable at least.
Thank you.
Hi, very nice talk, and the idea of style transfer at the end of the talk is very exciting. And it seems like the concept captures the concept of latent variable in the data very efficiently. And it also remind me of, the computer graphic model which use latent variable like location, rotation, in order to render the full image. So do you think we can use some idea concept of computer graphic model in deep learning and turn ConvNet into something like inverse graphic model or not?
Yeah, I mean, there's quite a bit of work on this. People who use graphic engines where you have the latent parameters, so you know exactly what the position of the chair you're generating, and that way you can generate a pair of images. Here are the parameters of the chair. Here's the image of the chair. Train basically what amounts to a deconvolutional net or reverse convolutional net to produce the chair. Generally, also with a mask. Otherwise, you get kind of fuzzy boundaries. I think there is work by is that Thomas Brox or Matthias Petke? I can't remember. One of the two. About this that was early on. There's work at Microsoft Research in Cambridge. There's quite a lot of work in this area. In fact, kind of an explosion of this in recent months. So that's supervised. And it uses a graphic engine. There's also interesting work, at least two different ones that I know of attempting to build a differentiable graphic rendering engine. So Michael Black at Max Planck Institute has something like that, which you can directly backpropagate gradient through the graphics engine. And there is also some work out of Oxford in Roberto Cipola's group on kind of the same idea. So I think those are really cool for, basically image generation in supervised mode. But sometimes you have to stick with natural images, and you don't want to use synthetic images.
Thank you.
Okay, let's thank the speaker again.
Thank you.